This is the 5th episode of Poke A Mon, where real science meets the Pokemon universe. I'm Kyuka, but you can call me Professor Baobab. My expertise is in science communication. You can sign up to my weekly newsletter below to get access to a free step-by-step guide on how to master any subject so you can explain it with ease. Disclaimer: this podcast is in no way affiliated with the Pokemon Company, Game Freak, or Nintendo. I am using Pokemon as a pedagogical tool as it pertains to tangential learning. In other words, I tell stories using Pokemon to capture the attention of those interested in Pokemon while remaining integral to the presentation of scientific knowledge. Today I'll be talking about thermodynamics and a little bit about how Charizard produces its Flamethrower. This episode is going to be rather long, but nevertheless it's not going to be exhaustive. Thermodynamics is the branch of physics that deals with heat, energy, and the ways they transfer and interact within systems. It explains how energy changes form and how these processes govern everything from the temperature of objects to the efficiency of engines. In essence, thermodynamics helps us understand the flow of energy in the natural world, from simple heating and cooling to complex power generation systems. The word thermodynamics comes from Greek. Thermo means heat and dynamics means force. The study of thermodynamics as we know it began in the early 19th century when the relationship between heat and the capacity to do work was realized. Thermodynamics was a huge part of my material science and engineering studies at Imperial College London. The reason for this is clear. The biggest goals in engineering is to optimize designs for better performance, to reduce cost, and to lessen the extent of environmental degradation. Thermodynamics often provides the keys to achieving these goals. There are two kinds or views of thermodynamics. If you look at the grand scheme of particles behaving as a gas, liquid, or solid, but not at the particles at a granular level, you would be doing classical thermodynamics. However, if you were concerned about the behavior of particles and how they are related to the structure of matter, then you would want statistical thermodynamics. It's called statistical because it tends to calculate the average behavior of particles in a system. Statistical thermodynamics demand a higher level of mathematical complexity, so we're going to focus on classical thermodynamics. This will be enough for studying most systems. If you are currently studying thermodynamics, you may hear the word system a lot. Simply, a system is the thing being studied. For example, the circulatory system is a well-defined system, and you can analyze the pressure in arteries, for instance. However, an engine is also a system. A refrigerator is a system. A neutron star is a system. So a system is simply anything you want to focus your attention on. When you have a system you are studying, you assign properties to the substances in the system. For example, if your system is Charizard, you could say Charizard's skin is a thick, heat-proof, flexible material. This way, you could assume that a negligible quantity of heat escapes from Charizard's body into the surroundings. Now, the surroundings doesn't just have to be the surrounding air. We can easily use surroundings interchangeably with outdoors and environments, but engineers use surroundings in the broadest way possible. The surroundings is simply anything that is outside of the system being studied. Finally, a boundary is the layer between the system and the system's surroundings. It could be in motion. For example, if Charizard were breathing, the volume inside its body would change and there could be work being done. I will discuss work done later. I want to focus on definitions for this chapter. A closed system is a system that always contains the same number of particles. A closed system can exchange heat with its surroundings, but not mass. Charizard would be described as an open system, the opposite of a closed system, as it can breathe out particles that were once inside it. An isolated system, on the other hand, is a system that does not exchange heat or particles with its surroundings. It is fully isolated from its surroundings, hence the name. I've mentioned things like mass and volume. These are known collectively as properties. In thermodynamics, a property is a particular characteristic of a system. A property always can be assigned a numeric value at any point in time, and it doesn't matter what state the system was in previously. A state describes the condition a system is in as a result of its properties. If a property changes, the state would change to reflect this. When a property changes, the system is said to have undergone a process. Knowing just a small number of properties is typically enough to determine the remainder of a system's properties. Of course, not all quantities are properties because the values of some quantities, such as energy transfers, are dependent on the history of the system. Technically, a quantity is a property only if a change in the value of that quantity does not depend on the details of the path the process took to cause the change. If we combine some of this new language, we can define a thermodynamic cycle as a series of processes that take a system to the same state it started in. This means that all the properties would have the same value they began with. This doesn't mean nothing happened. It means that after everything that did happen, there was no net change in the value of any of the properties in the system. We will explore this concept more later, but I just wanted to furnish you with the definition so you would be more prepared for when I talk about this in more detail. So far, I have mentioned that a property is a quantity whose value does not change depending on the path a system took to move from A to B. However, there are two categories of properties: extensive and intensive. Mass and volume are extensive properties because the value of an extensive property in a system is the sum of the values of the property in every part of the system. So, Charizard's mass is the sum of the mass of its circulatory system and its cardiovascular system, etc. However, Charizard's body temperature is not the sum of the temperature inside its heart and stomach, etc. Therefore, properties like temperature are known contrarily as intensive properties. Their values do not depend on the size of the system and can vary spontaneously in different regions of a system. This next definition is for a term I would hear ad nauseum while I was studying material science. See if you can guess what the term is from the definition. A region of material that is chemically and physically homogeneous. In school, you probably come across this term as state of matter. The answer is phase. The difference between a phase and a pure substance is that a phase can be made of different kinds of particles, whereas a pure substance must only be made of one kind of particle. However, a pure substance does not have to be in the same phase, so liquid, water, and steam can be described as a pure substance if they are the only two phases in a given system. Last but not least, equilibrium. Equilibrium comes from Latin equi, meaning equal, and libra, meaning balance. Equilibrium simply refers to a state of balance. an equilibrium state, if you will. The concept of equilibrium is vital in classical thermodynamics. Examples include thermal equilibrium and phase equilibrium. Equilibrium can apply to two systems, a system and its surroundings, or a system undergoing a process. This brings us nicely into a discussion of the various laws of thermodynamics, starting with the very last one to be discovered. Although the fourth law of thermodynamics was discovered in the 1930s, long after the first, second, and third laws were already well established, it was so fundamental that it had to come before every other law. So it is also known as the zeroth law of thermodynamics. Temperature is difficult to define under the macroscopic view of classical thermodynamics. However, we can access a solid understanding of thermal equilibrium. Consider the following illustration. There are two metal blocks in front of you. They are made of exactly the same metal. Let's say they're both made of copper. If you pick them up, you may feel your hands get colder. This is the feeling of thermal energy leaving your hands and going into the blocks. However, after a minute or so, the blocks would no longer feel cold to touch. This is because the level of thermal energy at the surface of your hands is identical to that on the surface of the blocks in contact with your hands. Also, since copper is an excellent conductor of heat, we can safely assume the temperature of the blocks is the same everywhere, since the thermal energy is able to quickly spread evenly throughout the blocks. Congratulations! Your hands are now in thermal equilibrium with the copper blocks. Furthermore, if you place the two blocks together, even though they weren't in contact before, they too would be in thermal equilibrium with each other. Using this allegory, we have deduced the zeroth law. If two objects are individually in thermal equilibrium with something, those two objects are in thermal equilibrium with each other. This is the law thermometers obey every time they are used. If you place a chicken inside an oven at a particular temperature, you can kind of guess when the chicken will be done. However, if you want to know whether the temperature in the chicken is the same as the temperature of the oven, you can take the chicken out and measure the internal temperature using a thermometer. If the temperature is at the same temperature as the oven, you can thank the zeroth law of thermodynamics for knowing that it means the temperature inside the chicken has now reached the oven temperature. Energy flows from hotter sources to colder sources until thermal equilibrium is achieved. That's the crux of the zeroth law. Well, what is energy though? It's a fundamental concept in many academic fields, thermodynamics included. Yet, we still don't have a compelling definition of energy. What I learned is that it is the capacity to do work. However, this only tells you that it isn't the same as force or work itself. It's almost a recursive definition, since work and energy are intimately related anyway. Energy can be stored unlike work. Energy can be transferred by work. Energy is such a confusing topic that UK education systems are pushing for a shift in the language used for energy, from types of energy to stores of energy. The idea is that it's simply a universal unit of energy measured in joules, and kinetic energy, chemical energy, and the like are contrived expressions of the same universal energy stored in different ways that afford students the ability to solve problems concretely. If energy is the capacity to do work, work is the transfer of energy through a force acting over a displacement. In a thermodynamic context, because that was mechanical, in a thermodynamic context, work can be done by a system on its surroundings and can be interpreted as imparting a force to an object. Let me make this clearer with an illustration. Charizard can use the move Flamethrower. Before it uses the move, the energy is stored inside Charizard's body as chemical energy. The chemicals inside Charizard's body have the capacity to liberate and release their energy in the form of Flamethrower. Now, when Charizard finally uses Flamethrower, the heat energy is transferred from inside its body to whatever Charizard's target is outside its body. This Flamethrower is a plasma being moved with force. Briefly, a plasma is a phase or state of matter composed of charged particles. Any fire or flame you see is a plasma regardless of how hot it is, whether it be from a candle or the sun. Anyway, the plasma is ejected with a great force that moves it a great distance, that moves it a great displacement. In other words, work is done on the plasma particles. This work could be done thanks to the capacity of the chemicals inside Charizard to do the work. While the formulae for the different changes in energy can be derived using calculus, for instance, the change in kinetic energy is a half of the mass multiplied by the difference between the final velocity squared and the initial velocity squared, there is a property which must be conserved in any system without fail. The formulae only allow us to deduce certain states we might be able to find a system in, provided everything else is kept constant, such as assuming effects of air resistance can be discounted. This is the law of conservation of energy, and it is neatly and completely expressed by the first law of thermodynamics, which states that the change in energy contained in a closed system must be equal to the net energy transferred into the system, which is heat in, minus the net energy transferred out of the system, which is work done. In short, energy cannot be created or destroyed. Work is unlike energy and the other properties in that its value depends on the details of the process that takes a system from one state to another. As a result, it is not possible to find an exact differential using calculus because we cannot issue values to the work simply at the final and initial states. For this reason, work cannot be a property of a system. In virtually all depictions, Charizard uses Flamethrower as forcibly as possible. However, if it were to use Flamethrower slowly, it would have a different effect, even if it expelled the same volume of plasma. The reason for this is that work is being done by Charizard to expand the air. The slower the expansion of the air, the closer to equilibrium the process is, the more well-defined is the state of the system of the expanding air per increment of time. In short, the more forceful the Flamethrower, the faster the change in volume because of the sudden increase in the number of fast-moving particles. As a result of an explosive change in volume, there will be a time delay while the surrounding air particles move out of the way. This will result in a smaller overall change in work compared to if Charizard used Flamethrower in quasi-equilibrium, meaning that it would allow the air to be at equilibrium with the Flamethrower at all times. However, this is an ideal situation since Charizard would have to sustain the Flamethrower for an extremely long time, possibly forever, to achieve this. Perhaps it would be more intuitive to provide a mechanical example. You probably learned in high school physics that work is force done over a displacement. While force and displacement are vector quantities, work is a scalar quantity. This means force and displacement are dependent on the direction they are applied, as well as their size, while work only depends on its numeric value. Let's say Charizard uses Flamethrower on a building. If Charizard just stood there and used Flamethrower, it would probably burn down the door and little else. If, on the other hand, Charizard used the same Flamethrower with all the same intensity and duration, but flew around the building, it would probably inflict more damage that way. Meanwhile, properties like the energy and volume of the particles from the Flamethrower would be the same regardless of the details of the process. If you recall the definition of work, it is sufficient to think about the effects of work as pushing an object through a displacement. This correspondence between thermodynamics and mechanics allows us to use the same equations we would use in mechanics to solve thermodynamics problems. Don't feel like you have to understand the concept of work and energy comprehensively. As long as you can somehow discern there is a distinct relationship between work and energy, this should suffice for the final discussion regarding the first law of thermodynamics. This relationship between work and energy is an extensive property called internal energy. Typically, it makes more sense to consider changes in internal energy. The internal energy can be interpreted as the sum of all the kinds of motions particles exhibit, including all chemical bonds, intermolecular forces, and so on. Sometimes no work is done in an interaction. Such interactions are heat transfers. Heat is also not a property. You might wonder what work and heat are if they are not properties. They are called path functions because they depend on the path that took the system from one state to the next. No work is done while the burning gases are in Charizard's body, for example. However, heat is being released to the surroundings via body heat. For anyone studying thermodynamics currently, heat transfer is taken as positive if the heat is transferred into the system. This is in contrast with the convention for work, whereby positive work is done by the system on its surroundings. The reason for this discrepancy is that the sign conventions were established at the time of the steam engine, where it made sense to have such conventions. Heat can be transferred in a number of ways. You may be familiar with these modes: conduction, radiation, and convection. Conduction is a transfer of energy between more energetic particles to less energetic particles in a material or between materials. The rate of energy transfer through a block of material is directly proportional to the surface area of the block. The temperature gradient existing at a distance into the block and the thermal conductivity. This relationship is known as Fourier's law, after French mathematician and physicist Joseph Fourier. All matter above absolute zero emits thermal radiation. Thermal radiation is contrasted with conduction in that conduction requires a medium. The energy released via radiation per unit time by Flamethrower or any other similar move is given by the Stefan-Boltzmann law. This law demonstrates that the rate of heat transfer is proportional to the fourth power of the absolute temperature, which is measured in Kelvin, as well as to the surface area of the emitter and a property of the material called emissivity that defines how well the surface acts as a radiator. This surely makes sense. Charizard's Flamethrower would release more energy in 1 second compared to Charmeleon's Flamethrower, as Charmeleon would have a smaller throat, hence a smaller surface area. It's also interesting to note that if the Flamethrower's temperature were to double, the rate of heat transfer would increase by 2 raised to the 4th power, or 16 times. Finally, convection. Suppose there is a temperature gradient in a body of moving fluid. A fluid could be a liquid or a gas. Convection is just a combination of conduction and fluid motion. The rate of energy transfer can be quantified using Newton's law of cooling. Simply, the higher the difference in temperature between one side of a fluid and another, the faster the warmer side will be cooled. Have you ever wondered why heat flows from a hot object to a cooler one? It seems obvious, but why is it that cold objects don't transfer cold or coldness to warm objects? In short, inverse processes seem to not happen at all in nature. For example, it is not possible for Charizard's breath to return to its body. It is not possible to recall the damage caused by a flamethrower, and it is not possible for Charizard to evolve in reverse into Charmeleon. That is, unless the alga reversed the direction of the so-called arrow of entropic time. Otherwise, these are irreversible processes. Entropy, which is the quantity of energy unavailable for work, well known as being a measure of random disorder in a system, is effectively the only universal time-dependent property scientists have discovered. Yet it governs everything about the natural proceedings of the universe. Indeed, there is no process not affected by entropy. As such, we arrive at the second law of thermodynamics. Events that happen naturally are said to happen spontaneously. All events must increase the entropy of the universe, as surely as all events must start at an earlier time than when they finish. Thanks to the second law, we cannot have perpetual motion machines, even if they may not necessarily violate the first law. There are two famous definitions or statements of the second law. One is by Rudolf Clausius, the other is by Max Planck and Lord Kelvin. The so-called Clausius statement of the second law of thermodynamics states that it is impossible for a system to undergo a process such that the total effect is for a cool object to heat a warm object. A refrigerator works by transferring heat from a cool interior to a typically warmer item. However, simultaneously there is a radiator at the back of the fridge that transfers even more heat to the surroundings. The Kelvin-Planck statement is equivalent, but requires a brief refresher on the definition of a thermodynamic cycle. A thermodynamic cycle is a series of processes that takes a system from one state to the very same state. The Kelvin-Planck statement states that it is impossible for a system to undergo a thermodynamic cycle and impart work to its surroundings while receiving heat from an unquenchable supply of heat. There are several examples of thermodynamic cycles, but they fall into two main categories: power cycles and heat pump cycles. A power cycle converts heat to mechanical work. A heat pump cycle does the opposite. If we consider how Charizard produces its flamethrower, we can use language to describe the ideal thermodynamic cycle called the Otto cycle, which is normally used to infer how internal combustion engines operate. The first step occurs when Charizard takes a deep breath. The diaphragm lowers, causing the pressure inside the lungs to decrease below the pressure outside, which is what results in the air flowing into the lungs. This is called the intake stroke. A fuel source is also present in the lungs at this stage. This fuel could be made by certain reactions that happen inside Charizard's body and be introduced into the lungs via diffusion. In an Otto cycle, air is drawn in at constant pressure or is said to undergo an isobaric expansion. Next, Charizard holds its breath momentarily. Meanwhile, its diaphragm pushes up forcibly on the mixture of fuel and air to compress it. If we were to assume the gases inside Charizard's lungs is compressed without losing any heat to its surroundings because its lungs were effectively heat-proof, then this process, where no heat transfer occurs as the gas is compressed, would be called adiabatic compression. During this stage, both the pressure and temperature increase. The word adiabatic simply refers to processes where heat does not enter or leave the system. As a result, only work is done on the gases inside. After this happens, a surge of electrical impulses, perhaps from Charizard's nerves, provides the activation energy for the compressed mixture to combust. In an Otto cycle, this would be referred to as heating under constant volume, or isochoric heating. The word isochoric comes from Greek. Iso means constant and choric means space. In reality, some mass would be lost via diffusion or pushed out of the lungs due to the insanely high pressure. This explosion pushes the diaphragm back and causes the pressure and temperature to decrease somewhat. This can happen as an adiabatic expansion where no heat flows in or out. However, it is more technically accurate in an ideal Otto cycle to also say that entropy, which can be understood as a measure of disorder or the number of possible states the system can have, does not change. In this case, the process is said to be isentropic. Only an adiabatic process can be isentropic since heat flow is directly related to entropy in ways I will discuss a bit later. Finally, Charizard releases his Flamethrower. Two things happen. First, all the heat from the combustion products are released from Charizard's mouth. In an Otto cycle, this happens as an isochoric cooling process where the volume of the lungs does not change, but this is obviously not practical without Charizard simultaneously releasing the likely toxic combustion products from its body. So, while in an Otto cycle, an isobaric compression of the content of the lungs would follow, Charizard combines the two processes into one, in which its lungs cool down and relax at more or less the same time. I mentioned that the Otto cycle does not change the total entropy in the universe. With that, let me finish this challenging episode with a discussion on entropy. If you have received value from this episode, I would love it if you would leave a review. I mentioned briefly that the entropy change from a thermodynamic cycle is 0. However, why is that? Now, I won't get overly technical here. Rather, my aim is to provide a motivation for the existence of entropy as a distinct natural property that cannot be fully explained by the first law of thermodynamics. In statistical mechanics, which I will talk about superficially as our discussion on entropy could satisfy an entire episode by itself, the number of ways particles can be arranged in a system is an important feature of that system. The different states of each individual particle are called microstates. However, the property that indicates how many different microstates there could be is neither extensive nor intensive. This makes it unideal for calculations. However, by introducing the logarithm of that property, which is called multiplicity, we can create a function which is an extensive property. This function is called entropy. Meanwhile, it is more useful in thermodynamics to think about probabilities than of predetermined states. Therefore, by using calculus, it is possible to uncover a new interpretation for entropy. And that interpretation is given by none other than Rudolf Clausius when he devised the Clausius statement for the second law of thermodynamics in the late 19th century. Thus, the Clausius inequality states that the integral of the reciprocal of the absolute temperature with respect to the heat transfer at any location on the boundary of a system around that closed boundary has an upper limit of 0. If you googled Clausius inequality, you will see that what I just said is actually a very concise mathematical relation. The interpretation is that entropy either doesn't change or increases, so the entropy of the universe approaches a maximum value. Some features of the inequality are that 1. If a process is entirely reversible, namely an ideal thermodynamic cycle, the entropy change is 0. 2. Adding heat to a cold system causes a greater change in entropy than adding heat to a hot system. And 3. Even though changes in heat depend on the details of the process, changes in entropy do not. As someone who studied phases extensively at university, I couldn't finish without regarding the entropy changes during processes like evaporation and condensation. These are formally known as phase transitions, and although there are much more than just these two, I will only talk about these two before closing. Going back to statistical mechanics just a little bit, it probably would surprise nobody that there are more ways H2O molecules can rearrange themselves when in liquid water compared to solid ice. This is because in ice, there is less kinetic energy available for more ways for the molecules to move. Additionally, strong intermolecular forces further inhibit the freedom of the molecules. All this is to say that the entropy of a solid is always going to be much smaller than the entropy of a liquid. Now, if you consider a liquid and a gas, solids and liquids both occupy almost the same volume. However, those of you who have placed a mental sweet into Coke will recognize that gas occupies so much more volume than even liquids. Also, a gas that is left to freely roam around, and the atmosphere is essentially a perfect example of this, behaves almost like individual particles flying about independently of others, kind of like a noble gas. The particles do not exhibit any intermolecular forces and are absolutely free to move in any way that they want. This is how an ideal gas behaves. As a result, the entropy of a gas is far greater than that of a liquid, and the difference in the entropy between a liquid and gas is much larger than the difference between a solid and a liquid. In fact, it is only at absolute zero that the entropy of matter reaches its lowest value. This statement is so critical, it just so happens to be the third law of thermodynamics. However, this is where my textbook summary ends. Yes, I almost exclusively relied on the 5th edition of Fundamentals of Engineering Thermodynamics by Michael Moran and Howard Shapiro in researching for this episode. This was quite a challenging episode, but I talked about thermodynamics in quite some detail, particularly classical thermodynamics, although I did mention a little bit of statistical thermodynamics on the area of entropy. I talked about systems and defined some key terms with regards to systems. I obviously covered at least some details of the 4 laws of thermodynamics, particularly the first and second laws, and I talked about energy and heat and work. You can find the resources I consulted while researching for this episode in the show notes. Isn't the power of science simply amazing?